Wait, am I streaming onto YouTube right now?
Yep.
I am live.
I'm back.
And it's streaming my monitor. Alright. So I'm here. Okay. 0 watching. Alright. We're here. Yeah, here we are. Should I send it into the Whoopity Scoop Boys chat?
Yeah, I guess.
Because why not?
Yeah.
Hold on, where is it? Oh, there it is. Alright, we back.
Aha. Let me open up Clone Hero. Stop sharing your screen now on Discord.
Oh, is that taking up like a ton of space?
Yes.
So where do I do that? Aha, I think I see it.
All right.
Alright. Boss. I'm here. Okay. 0 watching. Alright. Wait, bro. Wait, is the stream just behind? Wait, what are you doing?
What am I doing?
Yeah, why can't I hear myself?
On my stream?
Yeah, I could hear something. Oh, am I watching my own stream right now?
Yeah.
So can I pause that?
Yeah, or at least mute. I would mute it.
Alright, I muted it. Alrighty, so here we are. So okay.
All right. I think we're good to go.
I haven't gone to paint yet. Should be streaming the stream. I don't know why I can't see paint on my stream right now.
Why do you need paint?
Well, okay, I'm supposed to be streaming my monitor.
And I'm not live yet, am I?
Boy.
What thumbnail should I use?
Ah. So it goes away for a second, then that's a good thing, actually. And that's what's streaming. Right? Yep. All right, sweet. So we're here with X's given theory.
What? Boy!
All right, so you can see my work that I've done here on this. So basically, this is a this is a stream. If you're wondering, this is a stream by a frustrated Algebra 2 student who doesn't understand why he has to show his work. So, I'm about to go off and show you guys why this proves that X is given, and I don't need to show any work. I can just say what X is.
Boy.
Alright. So consider the equation 6x plus 6x plus 6 equals the square root of 1,764. Right? Like, we know that x equals 6. Like, come on. The square root of 1,764 is 42. 6 times 6 is 36. Plus 6 is 42. 42 is equal to 42. But, let's just say you won't be getting full credit with most teachers if you just write x equals 6 and say it's given and move on. Alright. So, here's what I have come up with to show that x is actually given. So you do this part, the basic equation, right? And then you bring it down to 6 squared. You just square both sides, just to make sure, square both sides and then square root them both. So you get 6 squared equals the square root of 36, and you get 6 equals 6. Yeah, that checks out. You square both sides, 36 equals 36. That checks out. So there's a little bit of a check for you. You got the right answer. You got x equals 6. Now, you could argue that this equation is done, and it is. We found x. But why did we need to divide 36 by 6? Or, I guess I didn't write it in here, but I subtract 6 from each side. Why did we need to do that? So, when you're looking at why we need to do things to solve equations, it's not always necessary. So, for example, it's not always necessary, and there are parts of the equation that you could argue that are more complicated than you think. So, consider this. So you have x equals 6, but when you have an x by itself, there's always a 1 next to it. So x is actually never isolated. And so the problem with this is you get 1x equals 6, and you divide by 1 like I have here. You divide by 1 to each side, but you get the same equation. Nothing happens. You can multiply by 1. It doesn't matter. But why? So, but, and this is why it's impossible to isolate x, is because there's always a 1 next to the x, and so technically x is never isolated. But why is there always a 1 next to the x? So there's always a 1 next to the x because there's only one x. When you, like, let's say, like, right here, just like cross out the 1, and you have x equals 6, right? Now that's all fine and dandy, but the problem is that 1 is still there, and we know that 1 times something. Basically what this equation says is that 1 times something equals 6. Now, it's pretty obvious to everybody who has done basic algebra that x is going to equal 6, but technically it doesn't tell us that. And technically we can't find out, because there's always this 1. So what you have to do is you have to substitute what you think is the answer and multiply it by 1 and see if it balances. And in this case, 6 times 1 does equal 6. 6 equals 6. But the problem is it's always being multiplied by 1. Which means that it's...
We are alive. We are alive.
Which means that if it's always being multiplied by 1, then it's never done. You can do anything to this equation, 6 equals 6, as long as you do it to both sides. And the problem is 6 times 1 goes on forever. You see, you got 6 times 1 equals 6 times 1 over 1 equals 6 over 1. And you can just do that forever. You can just divide both sides by 1 forever, and nothing will ever happen to the equation, and it will always be the same equation. They'll always be equivalent. But the point is, you can still do stuff to it. And that's why it's not solved yet. You can even go ahead and cross multiply if you want. You get 1x times 1, or 1x to the first power, whatever you want to do with it. And then you get 6 times 1 to the first power, 6 times 1 to the billionth power, it doesn't matter. And you still end up with 1x equals 6. And because this is an infinite loop, the only way to solve this equation is to substitute. And that's what you're doing. What you're really doing is taking 1x equals 6 and taking the assumption that x equals 6 and plugging it back into 1 times 6, and you get 6 equals 6. So you're really checking the problem. But it's like this is what's traditionally classified as a check by many algebra teachers. Isn't really a check. It's more like actually part of the problem, because the check is kind of taught, at least in my experience in algebra, is kind of you finish the problem and the problem is done, but then you got to go back and check, and the check really isn't part of the problem. It's just something you need to do. But the problem is, it is part of the problem, because
boy, this is making no sense.
Because 6 times x. Are you watching, Ethan?
No, but I'm listening.
You're just listening? Well, yeah. Maybe if you were watching, it would make more sense.
Not really.
Well, you'd be able to see all my madness. You'd be able to see the work behind my madness. All right. Anyway, I can hear you playing Clone Hero.
You watching my stream?
No, I can hear you. I hear you though. Anyway, after we were so rudely interrupted by the man playing Clone Hero. Alright, so where were we? Ah, yes. I believe we were at 1 dividing forever, right, Ethan?
Ah, yes. Where was I?
You sound like Howard.
Ah, yes.
Alright, so I believe we're at the part we cross-multiplied. Right, so you cross-multiply here. Because again, this is my premise. It doesn't matter what you do to the equation. And it's still going to be the same. That's the thing. 6x plus 6 equals the square root of 1,764 is the same equation as 6 times 1 equals 6 times 1 divided by 1 equals 6 over 1. It's the same equation. But here's the thing. You don't know that. Theoretically. The thing of what you're taught is that you do not know what x equals by looking at this problem. 6x plus 6 equals the square root of 1,764. X equals 6. Like, let's say, for example, this part right here did not exist. And you just had, actually, let's say that instead of 6x plus 6 equals 1,764, you just had, or no, you had that. But then, instead of showing work, you just had x equals 6. There's a bunch of, so you can say it's a bunch of missing information. Algebra teachers would say, well, how did you get here? So, how you get here is, first of all, anytime you have a square root of a number, that is also given. Because it's the same as having the number. So, it's the same as having the number by itself, the number primed. So this number is 42, right? 42 squared. 40. Okay, hold on. 42 squared equals 1,764. This is a true statement. We know this is true. It's given. 42 squared equals 1,764 is a given value. But, so if that's given, so we know that x equals 6 because there's only one number. 6 times 6 plus 6 is equal to 42. And, like, you can write this all out, like, I can show all my work, minus 6, 6x equals 36. You can divide by 6, and then you're left with that pesky 1x equals 6, which can only be solved by substitution, obviously. But why is this necessary? Like, you always think, so the idea of an algebra, of expanding and contracting equations, is what we're doing right now is we're contracting this equation. 6x plus 6 is equal to 42, and you're condensing the equation by subtracting 6 from each side. You just removed a term from the problem. Well, that's misleading. You could argue that you did not remove any term, because you could write this equation here as 6x plus 0 equals 36. That looks, sorry, I wrote that horribly. But anyway, 6x plus 0 equals 36. But why? Why would you write it that way? Like, the 0 is, there's no reason to have the 0 there whatsoever, which is how you end up with that. Is you just remove the 0 because it's an irrelevant value. But what if I told you that the whole middle part of the equation was irrelevant? Like again, like think like right here. This equation here, I got all the work, and I can show it. This is the same thing. This is the same equation as this up here. And they are equivalent. It's equivalent every step of the way. 6 times 6 is equal to 36. 6 is equal to 36 divided by 6. So if x equals 6 is a given value, so like let's go look here. X equals 6 is given. We know what x is, because it has to be given because it's a 1x, and anything with a 1 by it must be given, because there's no way to isolate the number otherwise. So anything with a 1 next to it must be given. But what if you did a 2? 2x. So if you have 1x equals 6, 1x equals 6 is equivalent to 2x equals 12. It is literally the same equation. 1x equals 6 and 2 is equal to 2x equals 12, which means it's the same equation. Which means if 1x equals 6 is given, 2x equals 12 must also be given. Because they're both the same equation. But why? But like, so this is obviously, this is all a shortcut, and like you might look at my screen and be like, this is a shortcut. Like, come on. But it really is. This is a proof of the shortcut, because if you can work backwards and you can do an equation forwards and backwards. Like, for example, this equation, I came up with these numbers myself. I wrote this equation backwards. X equals 6 is given. Like there's only one number it can be, and yeah, it's, oh my god, what was I gonna say? Like, you can prove the given, because the 1 times 6 is equal to 6, and you get the 1 times 6 is equal to 6, which means that 1 times x is equal to 6. You can work backwards. 1x equals 36 over 6. 6 equals 36, which means that because they're all equivalent, they're all given. You still lost, Ethan?
Not lost, just
not paying attention?
Yeah.
Okay, I figured. Right, and so, yeah, and so, like, again, the whole reason that this exists is because my argument is that if you do it the traditional method, you can never solve an equation. Ever. Because you never have x isolated, and you're always working with given values. And so there's, I mean, and once you can do anything to both sides of an equation, you know it's done. And yeah. So there you go. X is given. And one of my arguments that's a little on the fringe side of things is that if you can do an equation in your head, it's given. That theory is not nearly as concrete as something like this, and is very, very, very subjective to the person. Now, again, it really just depends on the person. Like, some people are very good at mental math, and some people are not as good at mental math. Like you could take two people. One person is extremely good at mental math, and the other can do math, but, like, not very good at mental math. And, like, one could look at an equation and know the answer, and the other could be like, I have to solve this. But so it really depends on the person, but that can't necessarily be used as evidence, because it can't be applied to everyone. Like, mathematical concepts that are true, like, can be applied to everything that we know they can. They're like, oh my god, I'm like misspeaking big time. Like, mathematical concepts that we know are true, we know can be applied to a certain set of things. I mean, you could take this concept and make an argument that you say people who can do this in their head, that this is true for them. But that's not really true This just for these people it's given, and for these people it's not, because you're entering a big gray area there, and we don't want to touch gray areas. Well, yeah, actually we kind of do, because that's what we're doing here, but gray areas like that we just kind of want to leave alone. But like, again, like my logic here is entirely mathematic. Though doing an equation forwards and backwards can, like, showing about givens is all math. And again, like, you look at this x equals 6. Just remember now, when you see x equals, or any variable, this works for any variable, 1a equals 6. Or, like, you look at, like, a equals 6, 1a equals 6. Z equals 2, 1z equals 2. It works for any variable, and it's just that x is the most common variable, obviously, used in algebra. So, like, that's the one I was picking on, but, like, you know, again, it's just because of the infinite loop, like, you know, I'm even cross multiplying up here. And I'm really, and then again, this shows again, you can do anything you want to the equation. As long as you do it to both sides, then it won't change the outcome. Like, if I have x equals 6, or like 1x equals 6, I could multiply both sides by 3, get 3x equals 18, and divide it back down to 1x equals 6, and it doesn't matter that I did that whatsoever. It literally does not matter, because it will always equal the same thing. And obviously equations will always equal themselves, and they won't equal just x by themselves because there's a 1 there. And they will equal 1 times x. So there you go. There is my theory on why x's must be given in equations, and why the conventional method is a little